Hi students, welcome to ALPHORES e-learning chemistry classes for second year. The running chapter is organic chemistry and now we are in session number 48. In previous sessions we are discussing about the isomerism possible in carbonyl compounds, and just let us have a recall of the previous discussion. As we know, the carbonyl group is of creating two different homologous series. One is nothing but the aldehyde group and the other one is nothing but the keto group. And now this aldehyde group, that is simply we can consider as CHO group, is a terminal functional group, and because of being terminal functional group, it is not at all possible to find any positional isomerism in this. And just when it is of having this carbonyl group, say for example if it is C4H8O, not H8, it is H8O, we can write this as CH3, CH2, CH2 and CHO. This is with 4 carbons. Now this can also be written like this: CH3, CH3, CHO. And now in this case it is having 4 carbons in main chain, hence it is butanol, and in this case it is nothing but 2-methyl propanol. So when the carbon chain includes more number, that is nothing but in the two different aldehyde compounds, when the number of carbons that includes in main chain are different, so these compounds are said to be chain isomers. But you observe, this chain isomerism is possible in aldehydes only when there are 4 carbon atoms. In case of 1 or 2 or 3 carbon atoms, not possible to exhibit chain isomerism, is it not? And now functional group isomerism is not, that is a terminal functional group, and hence positional isomerism is not possible. So for aldehydes there is no positional isomerism. And then functional group isomerism, actually these two with the same, say for example C4H8O, we can write like this: CH3, CH2, C double bond O, CH3. This is now keto form, and this ketone and these aldehydes, any of these two is a functional group isomer with this form because it is keto functional group. Clear? And now these aldehydes and ketones with the same molecular formula, automatically they are exhibiting functional group isomerism. Clear? And now coming to metamerism, and you observe metamerism, already we know it is nothing but a special kind of isomerism where same molecular formula, same functional group, but different alkyl groups when present in the molecule, then they are said to be metamers. And just you remember, my dear students, that metamerism is possible only for divalent functional groups. Divalent functional group means which is of having valency 2. In this case, just you observe, already one valency is bonded with hydrogen, only monovalent. So in case of aldehydes there is no metamerism. Metamerism can't be expected in aldehydes, but in ketones being divalent, it can exhibit metamerism. And just in that metamerism, you remember, it is possible only when the compound is having 5 minimum carbons in it with 4 carbons. Say for example, already we write this keto form. Here these alkyl groups methyl ethyl present, no other formation is possible. But when it is C5, we can write like this: CH3, CH2, C double bond O, CH2, CH3. It is diethyl ketone. And now we can write methyl propyl ketone like this. And now in this case same functional group, same molecular formula, that is nothing but C5H10O, and same function group, but alkyl groups are different. When such phenomena is observed in these molecules, that is nothing but same molecular formula, same functional group, but different alkyl groups when observed, these two are said to be metamers, and the phenomenon is known as metamerism. And here just you have to remember, my dear students, just you remember, it seemed to be positional isomerism actually, because it is 1 2 3 pentanone, and here it is 2 pentanone. Seem to be, from IUPAC's name we can consider the position of the keto group is 2 and 3 positions. So positional variation automatically, in general we are considering they are nothing but positional isomers. But in case of divalent functional group, you remember forever, in case of divalent functional group, when different alkyl groups present, the priority should be given to the metamerism, not for position. So that's why here these two are metamers but not positional isomers. Already we discussed about that. And now our discussion is for these carbonyl compounds combinedly, that is for aldehydes as well as ketones, even though they are functional group isomers with each other, some special type of functional group isomerism is observed in these carbonyl compounds. That is nothing but Tautomerism. This is also known as Keto-Enol Tautomerism. Keto-Enol Tautomerism. And just you remember, it is also known as prototropism. Prototropism. It is another, a new word. Clear? What is Tautomerism? Just you remember, the carbonyl compounds which are of any isomers, not only carbonyl compounds, which are of having two forms, isomeric forms, which are interconvertible due to migration of labile hydrogen. Labile hydrogen. Labile hydrogen means mobile. Hydrogen migrates from one atom to the other atom, and the compound which is of having such type of labile hydrogen and which is of having more electronegative atom with multiple bond. Here these carbonyl compounds, which say for example it is aldehyde, acetaldehyde. And now let us consider one more, ketone, that is nothing but acetone. In this case, this hydrogen, that is nothing but alpha hydrogen, sometimes will migrate to this, and thereby the pi bond will be shifted to this, and hence it is forming CH2 double bond C, OH and H. And now you observe, this is actually aldehyde, but here you remember, my dear students, even though this is aldehyde group, this CO group when present, this form, the isomeric form is known as keto form. It is not aldo form, just you remember. Even though, no doubt at all, you know, and all these people know that it is aldehyde group, but when it is in aldehyde group CO condition, that form in this Tautomerism is known as keto form. And here also it is keto form. Keto form. And now this keto form, when one of the alpha hydrogen is migrating to more electronegative oxygen, it is giving this one, and this is nothing but having an ene. Ene means double bond, and OH, whole, enol is nothing but, ene means double bond and whole is OH. Both these two are present in this group, in this isomer. That's why it is enol, and that form is known as enol form. Here also, and just you remember, it is establishing an equilibrium between these two. It is in dynamic condition, and now when this labile hydrogen is coming back, and this bond will go to this, and it is forming this keto form. And here also, either this one or this one, when the hydrogen migrates pi bond shape, it is giving CH2 double bond COH and CH3. Here you observe, again it is having ene and whole, enol. Here also, when the hydrogen is coming back, this will migrate to this, and it is establishing back this one. Such type of interconvertible isomers, and just in case if it is functional group isomerism, is observed between, say, with the same molecular formula C2H6O, we can write CH3CHO, and it is of exhibiting one type of functional group isomerism where enol is present. And in case if it is of having either function group like this, and it is having CH3, CH2, OH, these two are also functional group isomers, no doubt at all. These two are functional group isomers. Here, sorry, it is C4, C2, H4. These two are establishing like this, and now we are considering one more, C2, H6O. In this case, it is exhibiting the two functional group isomers like this. Clear? And even when these two are functional groups, unlike that of these, there is no such interconversion. Interconversion is not possible in this functional group isomerism. So these are purely functional group isomers, but these are interconvertible functional group isomers. Such interconvertible functional group isomers, because of the migration of labile hydrogen, are known as tautomers, and that phenomenon is known as tautomerism. And here actually there are dyad system, triad system like that. Just here it is triad system. Triad system is nothing but the hydrogen is migrating between 1, 2, 3. 1, 3 atoms hydrogen is migrating. That's why this tautomerism, generally for aldehydes and ketones, we are considering triad system of tautomerism. Dyad system is also there. Just let me give one example, one familiar example to you. This is hydrogen cyanide. This can be, the hydrogen will be migrated to this, it is hydrogen isocyanide. And in such a case, between 1 and 2 atoms, the hydrogen is migrating. That's why this is the best example for dyad system of tautomerism. But we need not go for this one. Now we are having in our studies about this. Just you remember, in carbonyl compounds, because of the migration of one alpha hydrogen from alpha carbon to more electronegative atom, a different isomer will form, which is having ene double bond and OH group in it, which is combinedly known as enol. And that these enol and keto form, both these two are interconvertible functional group isomers. Such interconvertible functional group isomers, because of the labile hydrogen, are known as tautomers. Clear? And now let us go for the condition where we can expect this type of tautomerism. And thereafter, of these two forms, even though they are establishing this equilibrium between the two tautomeric forms, which is of more in percentage, that is nothing but of these two, which is more stable, which is less stable, how to guess? Just introduction part, because it is we are having only the highlighted point from this tautomerism. Sometimes they may ask the question, and we need not go for the details of this. First, let us consider the conditions required. The conditions required to exhibit tautomerism is, first one, compound should possess more electronegative atoms like nitrogen and oxygen. Conditions for tautomerism. Here, first of all, the compound should possess more electronegative atom like oxygen and nitrogen. And second one, it should possess at least one alpha hydrogen. If there is no alpha hydrogen, there is no tautomerism. So that is the reason why we can't expect any tautomerism in formaldehyde. Here it is not possible. And next, in case of benzaldehyde also, you can observe in benzaldehyde also there is no alpha hydrogen, and hence it is unable to exhibit. And in case of CCl3, chloral, it is nothing but trichloroacetaldehyde. Here there is no alpha hydrogen, hence do not exhibit tautomerism. And in case if it is like this, CH3, C, CH3, CH3 and C double bond O H like this, here also there is no alpha hydrogen, hence it can't exhibit tautomerism. So the required condition is presence of more electronegative atom with multiple bond. Automatically when it is more electronegative atom except halogens, all the remaining are having multiple bonds, and presence of alpha hydrogen. In all these cases, just what I am quoting are nothing but the examples without alpha hydrogen. When the second condition alpha hydrogen is not present, they are unable to exhibit tautomerism. But if they possess alpha hydrogen, at least one alpha hydrogen, that means here 3 alpha hydrogens present, and in case if it is, if we are considering like this, it is of having 2 alpha hydrogens, and in case if it is like this, even then it is of having 1 alpha hydrogen, and this is sufficient condition. More electronegative atom with multiple bond and at least 1 alpha hydrogen is present in all these cases, thereby they can exhibit tautomerism. Not only this one, even in ketones also, CH3, C double bond O, CH3, it can also have alpha hydrogen. That's why it can form tautomerism. It can exhibit tautomerism. Clear? And that is the compound should possess more electronegative atoms, nitrogen like nitrogen and oxygen with multiple bond, and at least one of the alpha hydrogen should present. Then we can expect tautomerism. Like this. Here there is no alpha hydrogen, hence no tautomerism. Here there are alpha hydrogen, at least 1 alpha hydrogen, hence tautomerism. But there are 2 exceptional cases where the 2 conditions are obeyed by the compounds, but still they are not exhibiting any tautomerism. Let me give those 2 exceptional cases because they are attracting some sort of interest for the paper setter to frame any question on that one. It is nothing but quinone, P-quinone, benzoquinone, like this. Here just you observe 2 heteroatoms with multiple bond, like more electronegative atom with multiple bond, and here you know this is hydrogen, and here also 1 hydrogen, this is here also hydrogen. This is P, benzoquinone. And next one more is P-imine quinone. This is nothing but like this. Here instead of oxygen, imine is nothing but NH with a double bond. P-imine quinone. Imine. Imine is NH2. Clear? Imine is NH double bond. That group is known as imine. Imine quinone. In these 2 cases, even though there are the 2 conditions obeyed by the compound, still these are unable to exhibit tautomerism. Do you know the reason? Just it is nothing but because of restricted migration of the hydrogen. That is the migration of the labile. There is no labile hydrogen, simply we can say. It is not having any migration because when it has to migrate, the bond has to be shifted to this. But at the same time, this is also offering this hydrogen. Like that, its migration is restricted by this. So when the opposite factors are equal, automatically that migration of hydrogen is restricted. That's why even though these 2 compounds are obeying the required conditions for exhibiting tautomerism, they fail to exhibit tautomerism. Clear? And one more, they may ask the question related like this. Say for example, this is simple ketone like this, or if it is ketone like this, keto form, and this. In all these cases, just you remember, keto form is more stable. keto form is more stable compared to enol form. That means that enol keto form, enol form existence is almost all 0. Here that enol existence is almost all 0, very less. Here also, here the reason is nothing but the bonding between carbon and oxygen is strong when compared to the bonding between carbon and carbon, like this. So when it has to convert like this, it requires more bond energy. But to convert from CC double bond to this, it requires less bond energy. That's why it is favored to be keto form is more stable. But there are certain compounds where we can expect enol forms are major in contribution. That is nothing but one of the best known example is nothing but in case if cyclohexanone is ketone is more stable, but if it is existing like this with a double bond, if it is like this, it doesn't exist in keto form, because when the hydrogen is migrating to that, it is now converted to phenol. Phenol is nothing but one enol form, and here it is getting aromatic character, and because of getting aromatic character, it is highly stable. And just you remember, so when it is forming this enol immediately, and here let me introduce one word, don't confuse. Here the conversion of keto form into enol form is known as enolization. And dear students, you remember, it is always enolization. Here enolization is almost 0. Enolization is almost 0. We should not consider that enol is converted to keto form and hence it is ketonization. There is no word related to ketonization. Just you remember, there is no ketonization word, just enolization. If it is going maximum, here 100% enolization takes place. And in case if it is not forming, then just we have to say that here 0% of enolization takes place. Like that only, either it is forming or it is not forming, we have to refer that formation only with the word enolization. There is no word related to ketone formation. Clear? That is about here the enolization is very less because of stable CO double bond. And in such a cases, there is enolization. Enolization is more because there the enol form is more stable. Clear? And now one more complex. It is sometimes they will ask the question, in case if any carbonyl group like this is having two types of alpha hydrogens, this is and this is, we can expect two types of enol form, this one and the other enol form is nothing but this hydrogen may involve, then it is CH3 COH double bond CH CH3. This is A and this is B. Now can you guess which is more stable, which is formed more frequently, readily? Just to remember, this is of involving, that is this alpha hydrogen, less alpha hydrogen carbonyl is involved in enolization. The reason is simple. Here it is forming more substituted alkene, but here it is less substituted alkene. That is the reason why it is of more stable and it is readily forming. Just like this they will ask the question. And one more is, in case if it is of having double bond O CH3, in such a case, this when involved in enol formation, just you remember CH3 COH double bond CH C double bond O CH3, this is of forming more enolization. Why? More enolization is because of intramolecular hydrogen bonding creates, or intramolecular hydrogen bonding is of giving some extra stability for the enol form, and compared to this it is of having less enolization. This is when these two are formed, it is very less content, 1% or 2% like that, but here it is of forming more percentage, nearly 70% of this enol will form. The reason is nothing but because of formation of intramolecular hydrogen bonding, that enol form is getting more stability. Clear? That is about the tautomerism, and just some sort of highlighted points related where some points which are attracting this paper setter. I discussed about all these things. Clear? And now there are in case of geometrical or optical isomerism, here there is no scope for geometrical isomerism, or in case if this type of, it is nothing but related to alkene, because when we are considering double bond C, you know, when different groups are present on the double bonded carbon, automatically they exhibit geometrical isomerism. And optical isomerism is also, we need not study separately, because in case of any carbonyl compound, any carbon is found to be of chiral, then we can expect the optical isomerism also. Like that, those isomerisms simply you can consider as usual by considering the double bond, restricted rotation, geometrical isomerism, and in case if any chiral carbon present, then we can expect optical isomerism like that. Clear? In coming sessions, directly we are going to the study of preparations and properties of these carbonyl compounds. Clear? Thank you.